Hello guys, this is Mr. Kennedy. Before we went on break for Thanksgiving the other day, we watched 3 videos on free body diagrams. So today I've made a video to show you how to determine the net force acting on an object using free body diagrams. Let's look at this first example. We've got the book sitting on the table. You might remember this from the test you took not too long ago. If you remember from the videos you watched, we began free body diagrams by drawing just one dot to represent one object in the system. So we had the book on the table. We want to know what forces are acting on the book. So here we have our little dot representing that. So I've drawn our dot here to represent our book. And so now we've got to represent the forces acting on the book. So the book is not moving. Do you think that means the forces are balanced or unbalanced? If you said they're balanced, you're absolutely correct. So that means there's no force acting on this book to make it move. So we simply have 2 forces acting on the book. You remember what this force is called? That'll be the force of gravity. We'll draw that on there in just a second. And then we have what we're going to call on free body diagrams, we're going to call these the normal force. So here we have Fg, or the force of gravity. Here we have force normal, or the force that opposes gravity. So the normal force always acts in the opposite direction of the force of gravity. Now there's some more complicated instances of that where the normal force doesn't act exactly in the same direction as force of gravity, but we'll cover those later. So let's move along here. So in this case, if you notice, I've tried to draw these arrows the exact same length. In a situation where we have balanced forces, these vectors, or these arrows, are going to be the same length in each direction. If we had an unbalanced force, what do you think would happen? That's right. One arrow or vector would be longer than the other to represent unbalanced forces. So let's move along to an example where we have the book in motion. So here I've drawn a hand, the book on the table again. This time we have a hand resting on the book, but the book still isn't moving. So what's our free body diagram going to look like this time? Well, we're still going to have our force of gravity. It's going to be trying to pull the book towards the center of the earth. Now, we have our normal force. Again, I've tried to draw those vectors the same length, and I think I missed it that time. Now, here's a new force this time. We have an applied force. We have a hand pushing on the book. The book's not moving. So why isn't the book moving? Well, if you remember from all the forces we've been studying, contact forces, we know that contact forces always come in pairs. So we must have a force acting in this direction. Now, we know the book isn't moving, so those vectors are the same. So this force, we're going to call this the applied force. And this force acting in the opposite direction is the force of friction. Once again, this is our normal force. This is our force of gravity. So all of our arrows should be the same length, representing the forces are equal. So our net force, keep hitting the erase button, so that's messing me up. So our net force equals 0. Alright, let's go to an example where the book is actually moving. Alright, one more time. We have our hand pushing on the book, but this time the hand is pushing with the force of 5 newtons, so the book is moving. So take a minute and think about what forces we're going to have. Okay, we always have the force of gravity, so there we go again. Next, we have our normal force acting in the opposite direction. Okay, once again, those arrows are the same. This time, we have our applied force. The book is moving with the force of 5 newtons. So we're going to use an arrow to represent that like that. That's our applied force. And again, we have our force of friction. Now this time we're going to draw this arrow shorter. And why are we doing that? Well, like we said, the book is moving to the right at 5 newtons. So that means we've overcome the force of gravity to make that book move. So we have to represent that by making this vector longer than the friction arrow. The book's not moving up and down, so we know that our normal force and our gravitational force are going to be equal. So that's why those are the same. So how do we calculate the net force? Well, we know that the force of the normal force is equal to the force of gravity because we have no upward motion or downward motion of the book. We know that force applied equals 5 newtons. So, in this instance, our net force equals 5 newtons. Let's look at one more example. So here we have a truck. We have a 500 Newton force acting this direction. And we have a 200 Newton force acting in the opposite direction. So which way is the truck going to be moving? Which vector or which arrow is going to be longer? You got it. The truck is moving in this direction because that force is larger. So, once again, whoops, let's do that a little neater. So, let's go right here. We have our force of gravity. I missed that a little bit. It's a little off. That's okay. We have our normal force. We know these two forces are equal because the truck's not flying in the air. It's driving along a road. Now, once again, we have our applied force of 500 newtons. And in this instance, we have our force of friction equal to 200 newtons. So to calculate the net force again, once again, we know there's no up and down motion, so the forces in those directions are going to equal 0. They're canceling each other out. Force net equals 500 minus 200. So we have a 300 Newton net force acting to the right. The truck is moving forward and to the right. Alright, that's all I've got for you for today. If you look in your Google Classroom now, you'll notice you have the forces of motion, you have the free body diagram worksheet to work on. So if you'll get started on that, I'll be around to check on everybody. Make sure if you need to go back and see some of this video that you go back and do that. See you next time.